Good morning, everyone. We're going to continue in Chapter 9 today. Just remember, we're going to go through Section 9.6 this week for Midterm 4 next Tuesday. And also a reminder, no recitations in person tomorrow. There's an activity and a video that you can watch and just very generically write your answers to get your points for the week. If you email that to your TA, information can be found in an announcement from me or in the recitation page or the recitation module. Okay, so getting back into like the difference between CO2 and water, if you recall last time we were talking about how, oxygen certainly more electronegative than carbon. So when we're picturing our Lewis structure of CO2, we're going to predict that our zero formal charged oxygen truly would build up a negative charge because it's more electronegative than carbon. So the oxygen atom is going to be pulling the bonding pair electrons closer towards itself. We demonstrate that or show that with a dipole arrow like we did back in Chapter 8. And then we have the other oxygen in the exact same situation, two lone pairs on oxygen, a double bond. So zero formal charge overall, but we know the oxygen is going to go partial negative because it's more electronegative than carbon. And so we're going to have a charge imbalance in this molecule where carbon picks up a partial positive charge. And the magnitude of that charge, this isn't too big of a detail, but it's going to be double that of the negative charge on O's. So if you have like say a 0.2 charge on each oxygen negative, then carbon's charge would be plus 0.4. And so, but one of the things that happens for CO2 is you have one dipole this way and another this way, and for the molecule itself, the dipoles cancel out. So we have no molecular dipole moment for the molecule CO2, despite the fact that it has two polar bonds, and two really polar bonds. And so the overall dipole moment of the molecule, one of the measures of the polarity of the molecule as a whole, is that the dipole moment for CO2 is zero. And so in some ways, if you can think of ways that molecules can cancel out their dipole moments, then the molecule will eliminate the polarity overall for the molecule. What this kind of means is one of the things we were talking about last time is if you put a positive charge somewhere near CO2, neither one of the oxygens is going to win the fight for that charge, and the molecule will just spin relative to the charge. It wouldn't be pulled into the charge. Now imagine the difference between CO2 and water. With water having bent bonds, it has bent bonds because it's in the tetrahedral domain. We're having four total pairs of electrons. We have 1, 2, 3, 4 domains. So this is in that tetrahedral domain. So it fits into the structure of looking like a tetrahedron. And so the lone pairs might be coming out at us, going into the page where the bonds are sticking straight down. And then the bonds certainly aren't at 180-degree angles relative to each other. The bond angle here is closer to about 104 degrees. If you recall, it's a little less than 109.5 degrees, which we expect for perfect tetrahedral. 109.5 is perfect tetrahedral. Water's angle is a little bit closer because the lone pairs are pushing those bond pairs closer together. And so anyway, certainly not 180-degree bond angle, and oxygen's still more electronegative. So zero formal charge for all these atoms in the molecule, but water, or the oxygen in water, is going to pick up the partial negative, and it picks up that sort of reddish color, indicative of having more electron density. And then the hydrogen atoms go partial positive and pick up that blue color for having lost electron density or having a positive charge. And so we have positive charge building up on this side, negative charge building up on the oxygen. Now we put water near a positive charge, the oxygen is going to be attracted towards that positive charge. So you're going to get a stronger attractive force between a polar molecule and a charged particle than you would a non-polar molecule and a charged particle. And where this really gets into some of the molecular properties of a substance that we talk more about in Chapter 11, the force of attraction between two adjacent water molecules is going to be much more stronger having this dipole moment than two CO2 molecules will have with each other. And so this helps us understand why CO2 is a gas at room temperature, but water is a liquid at room temperature. Water has stronger attractive forces. It takes more heat, more temperature to separate the water molecules. CO2 has weaker forces of attraction by being nonpolar, so it takes less energy, so lower temperature to separate its molecules. You can think once a substance gets to the gas phase, its particles are separated and aren't experiencing intermolecular forces. Now, these details here, this is getting into some chapter 10 to 11 concepts. So the aspects of what it means to be a gas, what it means to be a liquid, what the forces of attraction are that make something a liquid, how we can judge stronger versus weaker attractive forces. We'll be discussing those in more detail in chapter 11. But one of the key details when we get to chapter 11 is the identity of molecules that are polar have this stronger attractive force. Molecules that are nonpolar have that weaker attractive force. Okay, so one of the things we can do is kind of look at a molecule, sketch a Lewis structure. From a Lewis structure, we should be able to identify the molecular geometry for the molecule. We should be able to predict bond angles. We should be able to predict polarity trends. So let's see if we can do that for a few molecules here. Let's start with HCN. And so we always have to kind of go with the process, Lewis structure to geometry to then predicting angles and some, polarity trends. And so for doing a Lewis structure, we have to count up our valence electrons. And hopefully this is really easy at this point. We're just looking periodic table placement, counting the valence count. So 10 valence electrons for HCN. Carbon should be the central atom. Like generally speaking, we're going to give you H, then C, then N is the connectivity. If that's not the connectivity, it'll usually be really obvious in terms of like the exam questions and seeing what the choices are. So usually we're giving you the formulas in the connectivity order that they're connected, or showing you or telling you sometimes which atom is the central atom. If you recall, we had an example before in a molecule N2O, and like in parentheses it said N's the central atom. So a lot of times we don't want to hide to you what the central atom is. And so if we follow our usual Lewis structure rules, we would be at this Lewis structure here. Remember, you kind of start a Lewis structure with the central atom, everything attached to it, give an octet to the non-central atoms. And then you look at the formal charge on oxygen. 2 plus should have 4 electrons, only has 2. So we get the 2 plus from 4 minus 2. Nitrogen should have 5 for neutral charge, and the nitrogen atom has 7 electrons surrounding it for minus 2. And so that's not a great Lewis structure because we have high formal charges. We have the octet not being satisfied yet for carbon. So why don't we make a double bond? That kicks the formal charge down to 4 minus 3 for plus, 5 minus 6 for minus 1. And then why don't we do this again, make a second double bond. And so that kicks us down to 4 minus 4, and then 5 minus 5 for neutral for both the H and the carbon. And so let me re-sketch this too, just to be clear here. So HC triple bond to N, and then a lone pair on nitrogen. And so I mentioned previously that carbon often and almost always in nature when it forms a stable compound has 4 total bonds, no lone pairs. Nitrogen will often do this with 3 bonds, 1 lone pair. Oxygen does this with 2 bonds, 2 lone pairs. It just becomes a matter if the atom's making a triple bond like nitrogen is here, or if it's like ammonia where we make 3 separate bonds. So ammonia makes 3 separate bonds. So here we're just having nitrogen make 3 bonds to one other thing. So it gets those 3 bonds in one shot for a triple bond. Carbon, of course, has 4 total bonds. All these formal charges are neutral. Now, in terms of the Lewis structure, this is a good Lewis structure, and it's also a pretty good picture of what the molecular geometry looks like because I have 2 total domains, just like CO2 has. And so the 2 domains want to get as far away from each other as possible, which is shown within the structure I've already written. So the bond angle there should be 180 degrees for a linear molecule. So that's a linear molecule. So 180 degree bond angle. And it's going to be perfectly 180. When you have 2 domains, it's really, if it goes less than 180, then it's creating extra repulsions a molecule doesn't want to have. So the best thing it can do is be perfectly 180. And the reason why I'm kind of trying to think, is it a little less than 180, is it a little greater than 180, is because sometimes we do want to think if the lone pairs kick a bond angle to be a little less. So we do maybe want to think for some cases of some molecules, you might have thought a triple bond, does it repel the single bond in or out of that plane? It really can't do that because if it did, it's just creating more repulsions with it. So if you think if it's going to press the bond this way, well, it's just creating an extra repulsion with the triple bond. So 180 is actually perfect in the actual bond angle here. And then what do we think about the molecular polarity? Do we think the first question might be, do you think the bonds are polar in the molecule? Because for the molecule to be polar, the bonds should be polar. So you may just look and say, well, a CN bond, should that be a polar bond? So should the nitrogen or the carbon be pulling electrons towards itself, and which one? The nitrogen should do this because nitrogen's fairly electronegative. It's one of the 3 most electronegative elements. So of course it's going to be pulling electrons towards itself, creating a partial negative charge on the nitrogen, partial positive on carbon. There's not a tremendous difference of electronegativity between H and C. But it's certainly like what we want to have here for a 0 dipole moment is a nitrogen on the other side, which is impossible. There'd be too many bonds for carbon. But we want to be balanced perfectly with an atom that's equally as electronegative on the other side of carbon to balance out, to make the molecule nonpolar. We don't have that here, so this molecule is indeed polar. So the molecule is polar in terms of its properties. So we have a polar molecule. So you can identify if the bonds are polar, like CO2. CO2 has polar bonds, it just ends up being a nonpolar molecule. HCN has polar bonds, and therefore, because the bonds aren't canceling themselves out, is a polar molecule. Now if we look at ozone, so O3, now 3 atoms, you have to have them connected in this sort of a fashion here, and I'm going to almost think ahead of what this Lewis structure and the molecular geometry are going to look like by kind of already starting with a bent bond, so I don't have to necessarily resketch it. But if you remember here, 3 times 6 for our count of 18 valence electrons, we have this lone pair on the central O that we get to by counting the electrons first by distributing lone pairs around the O's. That's 16 electrons. And then we have 2 electrons left over that are placed onto the central atom. And so once I put those electrons on the central atom, and knowing and having seen this Lewis structure before, you guys may have remembered the Lewis structure too, I was already thinking this is going to be trigonal planar. Trigonal planar because I have 1 and then 2 and then 3 domains already. If I want to cap the Lewis structure off though, I might realize that my oxygen has a 2 plus formal charge. Because it's a 6 minus 4, should have 6 electrons, only has 4 closest to it. Let me show the 1, 2, 3, 4 electrons here. And then the outer O's are 6 minus 5, 6 minus 7s. So I should have 6 electrons for neutral charge, I have 7. So I have minus 1 O's right now. So why don't I make a double bond and kick the formal charge down to 6 minus 6 for one of the O's. And then I have resonance taking place over to the other oxygen, so I'd have 2 equivalent Lewis structures I could sketch. The real molecule, of course, would look like a composite, but the key is I still have 1, 2, 3 domains. So whether it's a double, single, and a lone pair, that's still 3 domains. So I have 3 domains, so a double bond is just 1 domain, a single bond is just 1 domain, and a lone pair is just 1 domain. And so that's going to kick that into the geometry for 3 total domains, which is trigonal planar. And so we should have a planar structure, so this should be all in one plane. And then the bond angle should be about 120 degrees for our oxygen atoms here. So our bond angle here should be about 120 degrees. But now the electron pairs closer to the oxygen is going to push the bond to be a little less than 120. So the bond angle should be a little less than 120 would be our best prediction of the bond angle in ozone. And now this is, I think, a slightly tricky question in terms of what do you think about the molecular polarity? Because you may look and say, well, I have 2 oxygen atoms. How can one of the O atoms win out over the other in terms of the charge? But the issue is that we have built-in charges. We have one of the oxygens is negative, the other one's neutral, and the other one is now +1 once we make the double bond and come up with one of our 2 best Lewis structures. If I sketch the other resonance structure here, now my formal charge is kind of flipped, but the central oxygen is still positive. So if you think of the averaging or the compositing, each oxygen in the real structure of ozone, where it's kind of the average of those structures, where it looks maybe something like this, and our 2 O's end up being equal in bond distance. So instead of one O being double, the other being single, the ozone bond distance is kind of right in between that. It's about a 3/2 bond. It's like a bond and a half instead of being a double or a single bond. And again, as a reminder, this isn't an averaging. This isn't it going from here to here backwards really fast or anything like that. This is the electron pair spreads across the 2 bonds simultaneously. So the issue is when I can spot resonance structures like this, when I can sketch 2 different Lewis structures that are identical to each other, the real molecule looks like the average or the composite and doesn't ever look like any one of the 2 resonance structures that I wrote. So it doesn't ever look like A, doesn't ever look like B, it always looks like this structure here. And then the charges on the O's are about -1/2 on each of the O's, because that's what they would average out to. And again, I don't think we would ask you that question. I don't think I would ask you for ozone, what's the average charge of the oxygens? But if I did, the answer to that question would be about -1/2. But the reason why I'm showing you this here is one of the O's is minus, the other one's positive. That's a charge imbalance. That's what polarity is. So polarity is when the 2 atoms somehow end up with different charges on the atoms. We have more red charge developing on these atoms and then more of a blue charge developing on this atom. If I put a positive charge here, those negative oxygens are going to head towards that charge and experience that attractive force. So this molecule is indeed polar. So ozone's polar because it has a charge imbalance, because it has different charges, because it has negative end and a positive end. And so we have like a dipole pointing towards that negative charge in the oxygens. So O2, if you go back to molecular oxygen, nonpolar. If you go to ozone, it turns out that it does have a dipole moment. Okay, OF2 is a molecule where we have a central oxygen, 6 electrons per oxygen, 2 times 7 for the fluorines, and 20 total electrons. So central oxygen. Again, I'm going to think ahead because when I sketch my structure here, my Lewis structure, I have lone pairs on the fluorines. That's 16 electrons. That leaves 4 electrons left over onto oxygen. Now, in terms of what this actually looks like and how we can sketch it, like how do you sketch a tetrahedron or picture a tetrahedron, I think goes something like this. So just picture your oxygen being the central atom, and then just think of how you would have 2 bonds that are approximately about 109 degrees. So it's a little bit greater than a bond angle than we would do for trigonal planar. So if I'm thinking trigonal planar, a little bit of a bigger bond angle, just slightly, but then these 2 bonds here, one's coming out at us, one's going back. So I don't think that's too hard to picture where one of the bonds is just wedging kind of outward and down and the other one is coming outward and down. So just think of how we're having an atom wedge out and downward. And then into these positions, we're just putting electron pairs. So let's put electron pairs in the plane here, and then let's put our fluorine atoms over here. So we're forming our fluorine bonds straight out of the plane, and then our lone pairs in the plane of our paper. And then the electron pairs are going to be forcing those bond pairs to be a little bit closer together than we would predict for 109.5 degrees. So the bond angle should be a little bit less than 109.5 for the fluorine to oxygen to fluorine bond angle. So when we give a bond angle, it's always for the atom. So it's like the F to the O to the F bond angle is a little bit less than 109.5 because those electron pairs are pushing those bond pairs together because of their greater repulsions that they have because the electron pairs are closer to their nuclei. And so now in terms of the polarity, do you think this is a polar molecule or a nonpolar molecule? Well, let's think of the relative charges. The fluorines here, if we go to this Lewis structure, the formal charges all the way around the molecule are 0, 6 minus 6 for O, 7 minus 7 for fluorine. So the formal charges are all 0, but fluorine's more or less a negative. So we get these partial negatives on the fluorine, not balanced on the opposite end of the molecule. Now, occasionally I would hear students think, well, the electron pairs are negative in charge. Electrons are negatively charged, of course. But the oxygen, where you need to think is, well, what about the actual nuclear center? Think about how much charge is building up from the nucleus that's making its way outward from the atom. There's a net positive charge on the O side of the molecule, a net negative charge on the fluorine side of the molecule. This bond here, this molecule is certainly going to be polar. Like we have negative charge on the fluorine side and a positive charge on the oxygen side. In order for this molecule to be nonpolar, I would have to have something like CF4, something that's tetrahedral that has the exact same atom in every spot of the tetrahedron. So if I had a molecule like CF4, CCl4, that was one of the molecules we led off with, then that molecule would be nonpolar. And I'll sketch one of those in just a moment just to make sure. In fact, we'll go through a lot of different geometries and their polarities here in a moment. So this molecule here should be indeed polar. So the only time we get a cancellation of dipole moments is like you have to think those 2 dipole moments pointing towards the fluorine do not cancel each other out because we don't have the opposing dipole moments on the opposite end of the molecule. So let me come back to like CF4 again, just to make sure we're seeing this. So 4 plus 4 times 7 for 32 electrons. So Lewis structure where we have our fluorines. And I'm already going to go straight to the molecular geometry because I know I'm going to get 4 total bonds. And it's going to be a tetrahedral molecule. And that's all 32 of the electrons. So of course, there's no electrons left over for the central atom. And so now when I'm thinking in terms of these dipole moments pointing towards fluorine, it's probably not an easy problem to mathematically see, but do you kind of get the idea how all these dipoles are just mathematically opposing each other? So in this molecule here, we work out and have an exactly 0 dipole moment. Just like CO2's dipole is all canceled, CF4 is all canceled. And so it's because we get the exact same partial negative charge on the opposite ends of the molecule. So the only thing I need to do to make a molecule like this polar is I just need to change one of the atoms. I just need to, in the case of OF2, change carbon to oxygen, get rid of the 2 bonds as a result, so I have OF2 instead. That's one way to make a molecule polar. But if I just took this molecule here and said, well, what if I put a hydrogen here? What if I put a hydrogen here? I could just have made one hydrogen too, but I just need to like perturb the molecule in such a way that I get two different atoms or a different atom somewhere in the structure. So if I look at this molecule here, this is going to be a polar molecule because I now have these dipoles pointing this way here that aren't opposed by these atoms here. Now this molecule here is polar. If I change this here to an F as well, so if I had like CHF3, that's polar. If I had CH2F2, that's polar. If I make, if I change this back to, an H atom, and then make this an H as well, then just have one fluorine, that's polar. But then of course, if I make this an H and they're all CH4s, and that goes back to being nonpolar. So it's all about having like a sort of balance of charge where we get a net charge that's more negative on one end of the molecule compared to the other. And so, just to kind of summarize, it would be like CH3F is polar, CH2F2 is polar, CHF3. These are all polar, and the two that are nonpolar are CF4 and CH4. So those two are nonpolar. Let's look at some geometry trends of the trigonal bipyramidal structure. So if you recall, trigonal bipyramidal and octahedral geometries, these are coming up when we have either 5 total domains. So 5 total domains is trigonal bipyramidal. Octahedron or octahedral is coming when we have 6 total domains. So our central atom here in the middle. And so for octahedral, we'd have, bonds in this sort of fashion here. So we'd have, like we mentioned before, a square bipyramid is another name for octahedral. And then we'd have trigonal. So we have the trigonal plane in the middle, making a bipyramid structure. And so for trigonal bipyramidal, we have this issue where we have, and we pointed this out last time, you might recall, that we have axial position atoms. So 2 atoms that are on the same axis relative to each other. And then we have 3 atoms that are on an equator that aren't on an axis together. So we have, in the case of trigonal bipyramidal, axial position atoms and equatorial position atoms in different environments, if you will. And then in octahedral, we actually have just all axial. So we have an axis here, an axis here, an axis here. So we don't have this issue with octahedral, where we only have atoms in the exact same environment. Now, why this matters is if I want to kick a lone pair into trigonal bipyramidal, it means I have a choice of where I'm going to put it. So if I put a lone pair, if I want to kick one of these off, so I have 4 total domains where I have 4 bonding. So if I have 5 total domains, 4 of them are bonding domains, and then 1 of them is a non-bonding domain. Where do I put the non-bonding domain? Do I put it on the equator or on the axis? And so for trigonal bipyramidal, we're going to choose to put it on the equatorial position, and that's going to be where the lone pair resides, is on the equator, and then but not on the axial position. So hopefully you can see, though, that if you chose to put the electron pair in the axial position, you would get a different geometry than if you put on the equatorial position. So when we were talking about like ozone being trigonal planar with a bent geometry, we didn't have this issue. There's only like all the 3 spots on a trigonal planar structure where 3 total domains are the same. The same issue with tetrahedral. Tetrahedral geometry, if you go back to the CF4 example, all of those positions, either up, down, out, in, all 4 of those positions are identical to each other. It doesn't matter which one you choose to put the lone pairs. Like if you go back to the CF4 example, or the OF2 example, where I was putting the lone pairs didn't matter. It's just maybe for aesthetics, made it easier to put them into the plane and the O and F bonds sticking straight out of the page. But in the case of trigonal bipyramidal, it does make a difference. Now in octahedral, if I'm going to have 5 bonding domains and then 1 non-bonding domain, it doesn't matter where I put it. I can put the lone pair here. That's exactly the same as if I put the lone pair here. That's exactly the same as if I put the lone pair over here, or if I put the lone pair going down. So if I'm putting 1 lone pair in 1 spot on octahedral, it doesn't matter which spots I choose. I'm going to get the exact same geometry no matter where I put it. And so now when I look at the different sort of molecules and some of their geometries that we get for having 5 total domains, if they're all non-bonding, of course that geometry is trigonal bipyramidal molecular geometry. So remember, we have electron domain geometry versus molecular geometry. If all the domains are bonding, then the two names are the same. So just like 3 domains all bonding is trigonal planar geometry. If you have 4 total domains all bonding, like CF4 was tetrahedral. And here, if you have 5 total domains all bonding, trigonal bipyramidal molecular geometry. But if you replace one of those domains with a lone pair, we put them on, as I mentioned earlier, on the equator. Now, what a molecule is going to choose is going to somehow try to choose whether putting them on the equator or the axial position, whichever one makes the molecule more stable. And it turns out the molecule has the least amount of repulsions with its bonding pairs and the electron pairs if it puts it on the equator. Now, something that's maybe not easy to see with this structure here is the name seesaw is the molecular geometry name. So I'm going to sketch SF4 is a molecule that does this. If you recall, SF4 is just a molecule with 4 bonds to fluorine, where sulfur has a lone pair. So we've done this Lewis structure before, but just a quick Lewis structure on why SF4 has 4 bonds to sulfur, and then a lone pair on sulfur just comes from 6 plus 28 for 34 total electrons. And so lone pairs around the Fs are only 32 electrons. And so that puts the electron pair on sulfur. And so for a Lewis structure, again, come back to the idea, when you sketch a Lewis structure, you're not always trying to predict molecular geometry. So if we're just sketching a Lewis structure, it's really not a flat molecule like we're showing it here. It's really going to look like it does here. Now, the way I would kind of picture SF6 is I'm going to draw the axial position in this direction here, and then these atoms here on the equator are pointed this way, and then my lone pair being on that equator with them. So kind of in a trigonal plane around the molecule. Now, when I sketch it this way, do you see how this looks like a teeter-totter? And so the seesaw name or teeter-totter name is just coming from the shape that that molecule takes and the way it looks. So if you can ever sketch a molecular geometry and just look at it and try to see, well, what does the shape of the atoms look like? Like, what do these atoms actually resemble in terms of their shape? That's where the name seesaw is coming from. And so seesaw molecular geometry is a geometry taken anytime we have 4 bonding domains with 1 non-bonding domain on the central atom. So of course that's 5 total, so still in the trigonal bipyramidal domain. If we then have a second pair of electrons, CLF3 is one of these structures. So again, I want to make sure that we can see from a Lewis structure why we do this geometry. So we've done this Lewis structure before. If we start with their lone pairs around fluorine, that's 24 electrons. But CLF3 has 7 times 4, 28 electrons total. And so we have 4 electrons left over on chlorine. And so how do we fit these electron domains around chlorine? Well, just think trigonal planar, or trigonal bipyramidal, I mean, and put lone pairs on the equator, and then put fluorines on the other spots. And so we continue to put electron pairs on the equator as opposed to using the axial position. And so the geometry, again, if you think there are other possibilities that this structure could have chosen, this is the geometry, though, taken anytime we have 3 bonding domains and 2 non-bonding domains, again, for 5 total. So still in trigonal bipyramidal domain, but we're putting 2 electron pairs on the equator. So if you structure this molecule and sketch it this way here, then you have an electron pair kind of coming out at us, and then one going straight into the page here. And so if we're picturing this molecule, if we're picturing the fluorines here, then the electron pairs are like over here. So we're just using 3-dimensional space for these molecules and trying to use it as well as we can so the electron pairs can spread out and use space as efficiently as possible to minimize the repulsions of the electron pairs and the lone pairs and the electrons in the bond pair. So this is all about just how the electron pairs and the bond pairs repel each other. And now if you notice this shape here, do you see how this looks like a T? And so we call this the T-shaped molecular geometry. And so you can predict T-shaped geometry anytime you have 3 bonding domains, 2 non-bonding domains. This is the shape of the molecule. Now let's think for a moment here about SF4, or let's even go back to PF5 for a minute, or PCl5. For PCl5, do you think that's a polar or a non-polar molecule? So if we're saying polar or non-polar, what do we think for PCl5? Well, we have bond dipoles opposite each other. Of course, those are going to cancel. We have bond dipoles on a trigonal plane. Those are also going to cancel. So we have a nonpolar molecule. So as long as we have the exact same atom bonded to a central atom, if it's linear like CO2, nonpolar. If it's BF3, trigonal planar, it's nonpolar. If it's CF4, nonpolar. So we just have to have this one central atom, the same atom in every spot So we have PCl5, the molecule ends up being nonpolar as a result. But now SF4, we create all these partial negative fluorine atoms because the bond's certainly going to be really polar. Fluorine's a really large negative atom, so of course fluorine's going to be pulling electrons towards itself. We're not countering with a charge where the electron pair is with a nuclei to balance out those charges. So this ends up being a polar molecule. So SF4 is polar because it doesn't have that fifth fluorine to balance out the charges and has a net pole. Now, in terms of these bond angles here, let's do a little bond angle prediction real quick. And there's a slide that'll show this again later too. But do you think that this internal bond angle is exactly 180 now? Because we have an electron pair opposite it. The electron pair is going to press that bond angle to be a little less than 180. So a little bit less than 180, the internal 120 degree bond that we should get for the internal two fluorines, it's going to be less than 120 because you have the bond pair pressing onto these bonds, exerting a greater repulsion. So you can sort of, whenever you have lone pairs, they're going to often shift your prediction on the bond angles to be a little bit lower than you're predicting. Just like here off ClF3, these lone pairs are going to be pushing these bond angles closer together. So instead of this being exactly 90 degrees, it's going to be a little less than 90 degrees. So you're going to be getting geometries a little bit off perfect. But I think being a little bit, like if you can predict a bond angle is a little less than 90, you can easily then predict that this molecule has to be polar. So if you have electron pairs shifting geometries around, you then are going to have a buildup of negative charge as a result and can hopefully predict that you have a polar molecule. If you have a perfect balance, if you look at PCl5, the bond angles are perfectly 90 and 120. There's no way that we have the exact same pair of electrons pressing on each other that you get off that perfect 180, perfect 120 on the equator position. So these bond angles here, perfectly 120, as long as imperfectly 90, as long as you have the exact same atom at every spot. Now, what about xenon F2? Not a common compound, and apparently at really low temperatures, you can get xenon to form some bonds. You warm this molecule up, it's gonna break those bonds pretty quickly. So xenon of the noble gases is one of the few that form stable bonds. I'm sure we could probably get radon to do this too. I don't know if it being radioactive just makes the experiments not as attractive to do in the lab. So presumably radon would be a better element to make compounds in xenon. As you get bigger in the noble gas side, it's gonna be a little bit easier than for the smaller noble gases to make bonds. But even this compound here is not good enough to bottle and ship. It's not like you can buy this compound. A lot of the other compounds we mentioned in this chapter, you can actually buy, ship, and just to give you a sense that those molecules are important enough that the structures exist. This exists, but in some abstract ways. So 8 for xenon, 2 times 7 for our valence count, so that's 22 electrons. So if you're picturing a central xenon with 2 fluorines, lone pairs on the fluorines, that's 16 electrons. That leaves 6 electrons behind. 1, 2, 3, 4, 5, 6. So we now have xenon with 3 non-bonding pairs and 2 bonding pairs. So of course that's 5 total. And so that's going to put 3 electron pairs, and the best geometry xenon F2, the way it minimizes all of its repulsions of those electron pairs and bond pairs, is with a linear bond. Okay, so the structures did have choices, but these are the choices that molecules adopt. So any molecule with 4 total domains, with 4 total bonding domains and 1 non-bonding domain is a seesaw geometry. 3 bonds, 2 non-bonding domains goes T-shaped, and 2 bonding domains, 3 non-bonding domains goes linear. So xenon F2 is back to linear. Now this will kind of go towards the prediction of the polarity here, but what do you guys think, polar or non-polar? Now, if you think about the bond angle here, so think about is this bond angle, is it perfectly 180 or is it a little bit different than 180? Turns out that it's going to be exactly 180 because it has electron pairs here, here, and here pressing on it. So you can imagine if the fluorines were like, we have an electron pair here, let's bend, then they're like, oh, well, there's electron pairs over here bending us back. And so we have to maintain a perfect 180 degree bond angle. So it's not going to be a little less than 180, perfectly 180. And that helps us, I hope, understand why it's a non-polar molecule. So we go back from a PCl5 being non-polar because of how its bond dipoles cancel. SF4, ClF3, polar molecules, but xenon F2 goes back to now having its 2 dipoles, only 2 dipoles canceling each other out. And so again, it's a nonpolar molecule as a result of just the way its bonds are situated and how those individual bond dipoles cancel out. And then for 6 total domains, these I think are a little bit easier in a way because octahedral doesn't have this issue where I can replace any one of these positions with a lone pair. With the trigonal bipyramidal, we almost have to kind of memorize or kind of understand that there were choices and the previous structures were the structures that were chosen. And so for SF6, that's one where all the domains are bonding. So of course I get 6 total domains. If I have all of them bonding domains, that's the octahedral geometry for something like SF6. So no lone pairs on sulfur, 6 bonds to fluorine. And then for BRF5 has a total of 7 times 6, that's 42 electrons. And so you can probably see that central bromine with 5 fluorines. Each of the fluorines with a lone pair, that's 40 total, so 8 times 5. So the 2 electrons left over are placed onto the bromine atom. And so I think it's really important if I were to say, well, what's the molecular geometry of BRF5? It's really imperative that we see that we get this lone pair here. So we have to see through the Lewis structure that you end up with a pair of electrons on bromine. And then from that, you would then say, well, if I have 6 total domains, because I have 5 bonds to fluorine, so I have 5 bonding domains, I have the 1 non-bonding domain for 6 total, I should be an octahedral domain. And so I can replace my lone pairs anywhere I want, here or here or here. It doesn't matter, they're all the same structure. So let's put them here down below. And so then what I get is this pyramid structure. If you recall, I could have called the octahedral square bipyramid. Remember how that was one of the possible names, square bipyramidal, like trigonal bipyramidal? Well, this only gets 1 pyramid, so we call this square pyramidal. And so hopefully you understand why we're calling the square, we get 1 pyramid, so it's square pyramidal as opposed to square bipyramidal. And so we get a square pyramid structure from the shape of just where the nuclei are or where the atoms are. So we're kind of naming the shape you get for the atoms as the molecular geometry name, though of course it depends on the electron pair being there. You know, I think there's an underlying thing that's really missed in the way we present this in the book, which is that in a way we're kind of supporting the whole idea of Lewis structures and the whole concept of Vesper kind of in one without realizing it. Like what we're really doing here is trying to say, if the molecule really looks like the Lewis structure, if we really have 5 domains and a lone pair, then they should repel each other into this type of geometry. And if it is this geometry, when we look at the structure of this real molecule, then we've kind of supported the whole concept that bromine has a lone pair, that these pairs of electrons in the bonds and lone pairs repel each other, and that we get some of the properties that you would predict. You know, like for example, if you said, is this molecule polar or nonpolar? What do you guys think? So polar or nonpolar? SF6 is nonpolar. I think that one's easy. So SF6 is nonpolar because all those dipoles cancel. You have 3 axial fluorines that are all canceling out in terms of their dipole moment. We lose the atom here, so we predict polar for BRF5, and then you go into the lab and you try to measure and see indeed it is a polar molecule. So what we're kind of doing is by supporting that this really is the structure of the molecule, that you can predict it based off the Lewis structure, based off the number of lone pairs, that you get the right polarity trends. Imagine in the example that you looked at the structure of BRF5 and found it was nonpolar, and that it really looked like a trigonal bipyramid. Then you would say, well, what the hell are we doing? Like you would say that our Lewis structure rules have to be wrong, and you would rewrite your Lewis structure rules. So kind of what we're doing here in this process, maybe without realizing it, is supporting that the Lewis structure, it's important to see where the non-bonding pairs, where the bonding pairs, they repel each other. We can predict the geometry, and then we predict it correctly. And then we predict the true structure of the molecule. We get the right magnetic or the right polarity trend, that this molecule should be polar, and hopefully make sense of the 2 models kind of blending together and supporting them. Okay, so then if we move on to xenon F4, so 8 plus 4 times 7, in terms of our count, 28 plus 8 is 36 electrons. And then we end up with a central xenon, 4 fluorines. Just making sure we see how many lone pairs xenon should have. So lone pairs are on all the Fs. So that's 32 electrons, 8 times 4. That leaves 4 electrons behind that we put onto the xenon atom. So 2 lone pairs on xenon, 4 bonding domains. And so then we're going to put those electron pairs opposite each other. We wouldn't put the 2 electron pairs 90 degrees relative to each other. They'd have a lot of repulsions. minimize electron pair repulsions if they're 180 relative to each other. And now, what do we think of our internal bond angles here? Should these be perfectly 90 degrees? Because they are here. In SF6, they're exactly 90. And they're also exactly 90 in xenon F4. You have two lone pairs equally pressing on those bonds in both directions that they have to maintain perfect 90-degree bond angles. If we look at BRF5 and think about some of these bond angles, they're a little less than 90 degrees. So instead of being exactly 90 degrees like they were in SF6 or xenon F4, they're perturbed because of the lone pair pressing and not being balanced by the same electron pair on the opposite end of the molecule, like xenon F4 has. Xenon F4 has two lone pairs pressing equally on those bond pairs so that they stay exactly 90 degrees relative to each other. And so predicting or seeing that these are exactly 90, hopefully that helps us see and predict that this molecule xenon F4 is perfectly nonpolar, meaning that those dipoles go back to canceling each other out because we don't have an imbalance anymore. BRF5 has a net negative charge on top of the molecule that's not balanced on the bottom end. So we actually have a big negative charge on the top end that's not balanced on the bottom end of the molecule. So you can think you have two dipoles this way mostly canceling, two dipoles this way, BRF5 mostly canceling. You have a dipole moment here not canceled opposite it. So you have a net dipole moment pointing straight up pretty strongly. That helps us, again, have another way of understanding maybe why we're calling it polar and the other two nonpolar. So nonpolar for xenon F4. So if you're predicting if you get the idea of predicting if the bond angles are exactly 90 or a little less than 90, if you're predicting the angles a little bit less, that's helping us understand that those molecules would be polar due to the imbalance in the molecule and the imbalance of charge that we'd have to get. So if you can perturb the structure in terms of pushing bonds around, then you're doing so by pushing the electron density around and creating or supporting the concept of a dipole moment and polarity. Okay, so hopefully when we look at structures, and this kind of just reviews, we've talked a lot about polarity as we were introducing these structures, but this was a non-polar molecule because our dipoles all cancel. So if you think of the bond dipoles in PCl5, they all canceled each other out for non-polar. SF4, lone pair. All it took was that one lone pair to kind of kick our structure now into being polar. So what we would need for SF4 to be nonpolar is we needed there to be a fluorine atom in that lone pair spot to balance out the charge that we don't have. And so once we put a lone pair there, we kick that structure into being polar. Same thing for ClF5 being polar, then back to nonpolar for xenon F4. And then we went nonpolar for SF4, bond dipoles all canceling out. Bond dipoles canceling out in xenon F4, and then not so for BRF5. Let's look at a couple bond angle trends. The first one we already talked about how a double bond, so we have 4 electrons here, and that's going to exert a greater repulsion on 2 electrons. So we have 2 electrons in the bonds to chlorine, 4 electrons in the double bond. The 4 electrons in the double bond are going to press the 2 single bonds to be closer together. So instead of this being perfectly 120, that this bond angle here ends up being a little less than 120. And these bond angles here, which we would have predicted to be 120, because CL, like you're predicting trigonal planar. Trigonal planar is perfectly 120. And so the double bond to single bond angle a little bit greater than 120. Again, because the electrons in the double bond, more electrons pressing the single bonds closer together. So it's kind of like 2 electron pairs repel each other the most. Electron pairs repel bond pairs more. And then bond pairs don't repel each other that much. And double bonds repel single bonds more than single bonds repel each other. So you can sort of rank order or kind of understand repulsions just based on how many electrons are in the bond or that lone pairs are closer to their atom exerting a greater repulsion. And so the same thing for SF4 where we have an electron pair in this spot here on sulfur, that electron pair is going to be pressing our bond angles to be closer together. So the bond angle caused, if you look at the bond angle this way, greater than 180, I like to think of this bond angle here being less than 180 the other direction, because the electron pair pushed the bond angle to be less than 180, just like this bond angle here is less than 120. Should have been perfectly 120 if it were perfectly trigonal bipyramidal, but it's a little less than 120 due to the lone pair pushing those bond angles closer together because that bond pair has greater repulsions. The lone pair has greater repulsions on the bond pairs than the bond pairs do with each other. So we can predict some of our bond angle trends. This, again, hopefully helps us predict, seeing these bond angles not being exactly, helps us predict that this is polar. And the other molecule, the COCl2, is also nonpolar. So this, or excuse me, both these molecules are polar based on these bond angles being not perfectly 120. If we go to a structure like BF3, where I'm looking at this structure here as being BF3, perfectly trigonal planar, and I'm seeing that these bond angles here are all exactly equal to 120 degrees, and it's not different than 120, it's not slightly less than 120, that this molecule here, these bond angles being exactly 120 help me predict that this is a nonpolar molecule. So kind of like seeing when bond angles aren't exactly as you would predict with the geometry can help you understand that the dipole moment's likely going to be polar. So if you're kicking the bond angles be different than what you predict off of a perfect geometry within that electron domain geometry, then that's also going to be kicking the polarity into polar as well. Okay, so putting together multiple central atoms, we can do this now. And more to the point, I think, becomes, when we sketch a Lewis structure, we're going to do this flat. When we write a Lewis structure, we've wrote Lewis structures like this ever since chapter 2. And so this is how you're going to see a lot of Lewis structures as you continue into OChem or even to other parts of Gen Chem, is that we're going to sketch a structure flat because it's easier to do that than actually sketching the true three-dimensional shape. But we have to interpret the shape of this carbon here to be tetrahedral. Why tetrahedral? Well, there's 4 domains, 1, 2, 3, 4. So when I look at that first carbon, it's not really like a square planar structure like it looks on paper. It's really tetrahedral. This molecule here is really going to be trigonal planar because there's 3 domains, 1, 2, 3. So the next carbon's trigonal planar, and this oxygen here goes back to being tetrahedral domain. I might think it's bent because there's 2 total domains. So it's going to be kind of bent in its appearance. And so based on the structure here, I can say for carbon 1, tetrahedral, carbon 2 here, trigonal planar, and the oxygen in the next position, so this oxygen here, tetrahedral in its electron domain geometry, and I can start predicting bond angles. Like if I said, what's this bond angle here look like? Do you see how you guys think it's 90? Like on a test, I hate the question when we show a structure like this because it's kind of a trick question. If I said, what's this HCH bond angle here? It's not 90 degrees. Like the structure looks like it's trying to show you it's 90 degrees, but that's because it's a Lewis structure that's not trying to show you three-dimensional shape. This bond angle here would be best described as being about 109.5 degrees for being tetrahedral. Just like this bond angle here is not 180 because I sketched it to be 180 on the paper, it's closer to 120 because it's a trigonal planar geometry. So trigonal planar is 120, tetrahedral is 109.5 degrees. And so for this molecule here, of course, this is acetic acid, if you recall from nomenclature. The real molecule would look kind of more like, if I wanted to sketch it, I almost always, at least for this class, when you get to OChem, you'll probably start drawing tetrahedral molecules and more arrangements than just this one. I just really like to kind of picture it this way here because it really helps me kind of see and understand. If I just sketch it the same way, I hope you guys can see and sketch the tetrahedrals too, but that we'd have a structure that looks kind of something like this. And these electron pairs probably coming out at us and going into the page. And again, I don't necessarily expect that you'd be able to sketch this, but I just want to show this. This is what the real molecule looks like, that we're sketching flat. So it's probably easier to sketch it this way, right? It's a lot easier to sketch it flat than to have to like write it three-dimensional too. If you're making an image for like a textbook, it's really hard to like sketch it like with the real molecular geometry name, but it's going to be much easier if we just can interpret the shapes of the molecules based off a flat or two-dimensional Lewis structure. We can also have you guys put the Lewis structure together, so like CH2, CH, CCH. So the way I would be thinking of this is CH2 first, and then go to a C with a hydrogen, and then go to a carbon, then go to another carbon, then go to a hydrogen. I'm just like linearly connecting like CH2 to a CH to a carbon to a CH. And then what I need to do is either like count electrons, so I can count having 4 for the carbon, so that's 4 times 4, that's 16 total electrons, and then plus 1 for the hydrogen, so that's 1, 2, 3, 4, so that's 20 electrons. Carbons don't tend to form lone pairs, so I'm probably going to make 4 bonds with multiple bonds. So I can use a double bond here and then a triple bond here, because that gives every carbon 4 bonds. So if I notice every carbon here has 4 total bonds surrounding it with this bonding environment. And I would, if if you think there's other ways to sketch the number of bonds, I don't think you can do so. This is going to be the only sketch that you can come up with. And to be honest, I don't think we'd show you a structure and have you write the Lewis structure. We'd probably give you the Lewis structure, but you can really start predicting or sketching Lewis structures just by the basis of carbon having 4 bonds. But so then in terms of the electrons used, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs of electrons. So that's 20 electrons. And that's the right number that I should have. So like if I were to show you this Lewis structure and say, is this the right Lewis structure for this formula? Or is it consistent with the formula? It is. You know, like it's like sometimes if we show you a Lewis structure and say, is this the right Lewis structure for this formula? One of the easiest double checks is the electron count. If the electrons don't count up right, if you look at the formula and say it should have 20 electrons and we show you a Lewis structure that only has like 18, then you know that Lewis structure has to be wrong. But anyways, once we have this Lewis structure, or like let's say it's given to us, we have this Lewis structure given to us, let's do the geometries of the first couple carbons. So this carbon here, is that trigonal planar? Is it tetrahedral? Is it linear? And the question is, how many domains are there about that carbon? There's 1, 2, 3 domains, so that's trigonal planar. And the bond angles are about 120 degrees. The next carbon here, call that C2, is also trigonal planar. The bond angles are again 120 degrees. The next carbon here, in fact, the next two, call them C3 and C4. These are both linear. Why are they linear? Because they each have 2 domains. So they each have just 2 domains. So 1, 2 for the 1, use a different color. So 1, 2 domains for the 1, and then for the other, it has, for this carbon here, 1, 2 domains. So 2 domains each, those are linear, 180 degree bond angles. Okay, so I want to look at a couple of Chapter 7 review problems. We'll get into some concepts of bonding in terms of bonding models, in terms of overlapping of orbitals. So we'll look at some of this information next time. So there's a set of, I think there's 5 problems for like Chapter 7 review, for like Chapter 7 lecture review problems. I thought we could look at a couple Chapter 7 review problems to wrap lecture up today. And so for effective nuclear charge, remember this is our main periodic property that gives us our periodicity. This is why we have repeating trends from left to right that reset with each row of the periodic table. Our effective nuclear charge increases left to right because the charge experienced by the outer valence electrons are primarily only blocked by the core electrons. And as you go from left to right, the core is constant. And so our effective charge increases, and then it resets itself being low with the alkali group, and then to high towards the halogens. And we get a slight increase from top to bottom. So it's not a very big increase from top to bottom, but we do get a slight increase in effective charge. And this is due to, as the atoms grow in size, the outer valence shell has some relative high probability of being relatively close to the nucleus. And this kind of comes back to those like weird like plots we were looking at in Chapter 6 of all of these things starting to add up and having a relatively high probability for those electrons being slightly closer towards the nucleus, and why you get a slight increase from top to bottom. And so if you're looking from top to bottom, iodine has a slightly greater effective charge. And if you're looking from left to right for sodium and chlorine, chlorine has a lot higher of an effective charge. So iodine and chlorine have the higher effective charges. So just remember the effective charge increases left to right, slight increase, not a very big increase from top to bottom, but a slight increase from top to bottom. What about size trends? So as our effective charge is increasing left to right, our atomic trend is that we get a decrease in size. So the atomic radius from left to right is that it decreases. And then we get an increase from top to bottom. As you go top to bottom, you're just going to bigger elements, more electrons, more repulsions. Of course, you're going to increase in size. And so for K to Cl, that's our left to right trend. So chlorine is going to be smaller from left to right, higher charge for chlorine. And so it's going to be smaller as a result of that higher charge its valence electrons are experiencing. But then as soon as we have charged ions, we have to then recognize that K plus, potassium has 19 electrons, lose an electron, that's 18. Chlorine has 17, add an electron, that's 18 electrons. Those are isoelectronic. We use proton counts. So we have 19 protons versus 17 protons. 19 protons for the same electron count pulls electrons in to be closer. And so potassium is actually smaller So K plus is smaller, and then chlorine is smaller. So K plus and are the smaller ones here. Now, cations are smaller than their neutral atoms. If you take potassium, lose the valence shell electron, of course K plus is smaller. If you take chlorine, add an electron in, you increase repulsions and it grows in size. And so anions are larger, cations are smaller, such that K is bigger than chlorine, but then chloride is bigger than potassium ion. Okay, so when you're comparing ions, use your isoelectronic series. Okay, that's a good stopping point for today. We'll look at the other 3 Chapter 7 review problems later. All right, guys, have a great day.